In 2024, the four largest tech hyperscalers spent a combined $250 billion on capital infrastructure. By 2026, that projected total will hit $750 billion. Big tech is issuing massive bonds to fund this build-out, driving investment at a pace not seen since the dot-com peak. This is a global industrial mobilization. This spending is happening despite a collapse in the unit cost of AI. API prices for frontier models have dropped by roughly 80% annually. A model at GPT-4 quality levels cost $60 per million output tokens in late 2022. Today, that same volume costs under $1.50. This chart captures the core economic contradiction. We see a sharp downward line representing those falling API costs between 2022 and 2026, plotted against a massive rising bar chart of the hyperscaler capital expenditure racing towards $750 billion. This is the Jevons paradox. Making a resource cheaper increases total spending by unlocking an exponential number of new reasons to use it. When inference prices hit 50 cents a million tokens, previously expensive workflows become viable enterprise tools. Most industry observers have focused on model training, the expensive one-time process of teaching a model, as the primary driver of this demand. But the massive upfront cost of building a model is being surpassed by the daily, recurring expense of actually running it. The bottleneck is now the massive scale economics of inference, serving the payload of the model to millions of users at once. For the last 3 years, the narrative of AI infrastructure belonged entirely to NVIDIA. Waitlists for H100 and Blackwell chips stretched for 18 months, while the company's market cap surged past every other megacap on the planet. In late 2025, that narrative began to shift. Alphabet's fourth quarter earnings revealed that Google Cloud's backlog had ballooned to $240 billion, with the company announcing plans to spend up to $185 billion on its own infrastructure in 2026. At the center of that expansion sits Google's 7th-generation tensor processing unit, a chip called Ironwood. Google co-designed Ironwood with a specific strategic target: the high-volume, repetitive workloads, where cost to serve matters more than general-purpose flexibility. This chip represents Google's bid to compete directly for the high-volume inference market, currently held by NVIDIA. In early 2023, a standard AI workload was a single chatbot interaction, one prompt, one response, and a few thousand tokens. This flowchart illustrates how that workload has evolved. On the left is that simple single-loop chatbot turn. On the right is an agentic workflow. This is a system that plans a task, calls tools, reads documents, executes code, and verifies its own work, often retrying multiple times when it fails. This complexity creates a massive compute tax. A single agentic workflow typically consumes between 20 and 50 times more inference tokens per query than a traditional chatbot prompt. Enterprise data shows this volume is already in production. By the end of 2025, Salesforce's Agentforce platform was processing over 3 trillion tokens, with customers executing more than 3 billion automated workflows every month. Microsoft Azure processed over 100 trillion tokens in a single quarter, with record volumes growing 5-fold year over year. Despite that growth, Azure reported $80 billion in unfilled orders. The company simply could not satisfy the demand because the physical power and compute capacity did not yet exist. For a hardware platform to survive this token tsunami, it cannot simply be flexible. It must be optimized for power efficiency and sustained throughput. That brings us to Google's Ironwood, a dual chiplet package co-designed with Broadcom. This table compares Ironwood to NVIDIA's flagship enterprise offerings. Each Ironwood chip delivers 4,614 teraflops of FP8 performance, pairs with 192 gigabytes of high bandwidth memory, and pushes 7.37 terabytes per second of memory bandwidth. For the first time, Google's homegrown silicon has reached parity with NVIDIA's flagship. As the highlighted cells show, Ironwood matches or slightly exceeds the B200 across peak compute, memory capacity, and bandwidth. Chips running at this density generate immense heat. In 2025, the wider industry began a massive pivot toward liquid cooling, with server adoption jumping from 15% to over 50% in a single year. Google completed this migration years ago. They have operated liquid-cooled TPU racks since 2018, using valve-controlled coolant flow that adjusts per chip based on the workload to maintain 99.999% uptime. This combination of hardware parity and mature cooling infrastructure is what allowed Google to drop its Gemini serving unit costs by 78% across 2025. At the scale of a modern data center, individual chip specs are only half the story. The topology of the entire network is the actual product. This diagram shows the Ironwood architecture scaling from a single chiplet into a superpod. This is a 3D torus network of 9,216 chips, drawing roughly 10 megawatts of power. While an NVIDIA GB300 NVL72 rack contains 72 GPUs, this entire Google SuperPod functions as a single logical unit. It delivers 42.5 FP8 exaflops of peak compute against 1.77 petabytes of shared high-bandwidth memory. Managing that data flow requires Google's Jupyter optical networking fabric. Jupyter uses optical circuit switches to dynamically reshape the cluster on the fly. This allows engineers to flow workloads between training and inference without taking the system offline. This zero downtime flexibility at the exafault level provides the reliability necessary for high-volume enterprise deployments to transition away from standard GPU infrastructure. We are already seeing the results of that transition. In October 2025, Anthropic announced that Claude would run on up to 1 million Google TPUs. This represents roughly $52 billion in total commitments. A company at the frontier of AI research is betting its future compute capacity on Google Silicon. Safe Superintelligence, founded by Ilya Sutskever, also named Google Cloud its primary compute provider. Today, 9 of the 10 leading AI research labs are Google Cloud customers. Negotiations with Meta went further, covering the deployment of physical Ironwood TPUs directly inside Meta's own data centers starting in 2027. This timeline tracks the TPU's journey from a 2015 internal project into an external hardware franchise worth tens of billions. From the Apple Intelligence disclosures to the Anthropic and Meta deals, the TPU has moved into the center of the AI hardware market. Packaging Ironwood as a system for third-party data centers is a direct assault on NVIDIA's core enterprise business. It turns the TPU from a cloud feature into a standalone hardware competitor. This hardware race is hitting a physical limit. Global data center electricity consumption is expected to double to 1,100 terawatt-hours by the end of 2026. The power grid is now the ultimate bottleneck for AI. NVIDIA maintains a significant advantage through its flexibility. It remains the primary platform for every new, unproven research idea or model framework. However, as AI deployments mature, companies are identifying the specific, massive workloads they need to run at scale. In this environment, the definitive metric for success is the number of tokens delivered per dollar per watt. For these known high-volume workloads, the vertical integration of silicon, networking, and software co-design provides a mathematical advantage that general-purpose hardware cannot match. NVIDIA will remain a titan of the industry, but the era where one company dictated the pace of AI infrastructure is over. Inference has reached a scale that requires specialized, hyper-efficient hardware. Ironwood is Google's answer to that demand.